So this is the last section we're going to do in Chapter 5, which has been about polar coordinates and vectors. So far we've looked a lot at polar coordinates, and now we're going to look at vectors. So Section 5.4 is titled Vectors, and it has a lot of objectives, but some of them are very small, so don't get overwhelmed. So the first objective is going to be to graph vectors, so you'll need graph paper. Then we're going to learn how to find a position vector. And this is talking about a position in space. How do you tell somebody where something's happening? Then we're going to learn how to add and subtract vectors two different ways. So the first way is geometrically, and then we'll do algebraically. The fourth objective is to find a scalar multiple. So we'll learn about what a scalar is. And the magnitude, oh, we've heard that word before, talking about complex numbers. The magnitude of a vector. Then we're going to learn how to find a unit vector. So this has the same unit meaning as the unit circle. There's a 1 involved there. Then we're going to find a vector from its direction and magnitude. That's where the polar coordinate connection is going to come in. And then we're going to use this to analyze objects in static equilibrium. So you can see how useful vectors are. So vectors are used to indicate quantities that have two things, magnitude and direction. So things like force, where it's how much force are you applying and in which direction? Because if you have a block like this and you apply the force this way, that's a whole different thing than if you apply the force in a different direction. Different things happen. Velocity is also represented by a vector because you can be going in this direction really fast, or you can be going this direction really slow. So the length of the arrow indicates the magnitude. So it gives you a quick visual reference of this is much slower than this. And the arrow's head indicates what direction is happening of whatever you're applying, force, velocity, lots of things. So we use this notation, or you can make an official arrow if you like to take longer, but I've made probably thousands of vector arrows, so it's sufficient to make a single barbed arrow to show that it's a vector. So when you're doing it in handwriting, you must put the vector arrow on there. You'll lose points if your vectors don't have arrows, because that's the only way we know you're talking about a vector. In a textbook, you'll see they just use boldface type, but we don't really have a way to do boldface. So if two vectors have the same magnitude and direction, we say the vectors are equal. So notice that each different thing we talk about, we have to talk about how do you know if two of these are equal? When you learned about complex numbers, you talked about how do you know if two complex numbers are equal? When you learned about polynomials, you learned how to decide if two polynomials are equal. So each new thing you learn about, that's an important thing to know of how do I know if two of these are equal? So as long as two vectors have the same length and direction, we say they're equal. So if this is vector v and this is vector w, we can write a math sentence that makes sense saying vector v equals vector w. Okay, so adding vectors geometrically helps to give us a sense of what's going on. So how I imagine this is if you have one person pulling on a rope this hard, and then you have another person that's pulling not as hard but in a different direction, it changes the net effect of what's going to happen. So you go from the tail of the first vector to the head of the last vector, and then you connect them, and this is the vector v plus w, a new vector. That's the sum of the other two vectors, and it's the net effect. So you can see that person w is changing the direction of the outcome and adding a little bit to the amount of force that's being applied. So some of the things you look at in engineering is things set up like if you have a ring and you have one person's pulling this way, one person's pulling this way, and one person's pulling this way. And then the question would be, if you have one more person, how do they need to pull so that the ring doesn't go anywhere? Okay, so the cool thing about vectors is you can move them around. So if this is vector v, and this is vector w, and this is vector p, you can draw v over here, and then you want to add w, so you put its tail to vector v's head, and then you put vector p at the head of vector w, and then you can see that the sum of v plus w plus p is this vector that goes from the tail of the first vector v to the head of the last vector p. So vector addition is commutative. You can see from this figure that if you do w first and then v, but those people are working together, it doesn't really matter who stands where. If they're both pulling on the same thing, it's going to have the same net effect, no matter if person one's on the right or person one's on the left. So vector addition is also associative of if you have u plus v plus w, associativity says you can do the u plus the v first and get that result and then add the w, or you can add the v plus the w first and then add the u, and you're going to get to the same result. So the vector negative v is the vector that's the same magnitude but the opposite direction as the vector v. So if this is your vector v, this is your vector negative v. It has the same tilt and the same length, but the arrowhead is on the opposite end. So we can define the zero vector, and we can define the operation of subtraction. So we say vector v plus the vector that's opposite of v gives us the zero vector, and notice they all have to have vector symbols on them. So the zero vector is kind of a strange character because it has no length, but we need it so that we can define subtraction. And it's also called the additive identity in the land of vectors. So when you're multiplying by a real number, the real number is called a scalar. So scalar is just a number. Scalars have magnitude only. So things like weight, height, altitude, those have magnitude only, no direction. So if we multiply by a scalar, alpha v, so see how important it is to put vector symbols on the vectors. So this is a scalar alpha multiplying the vector v. The only thing that happens to the vector is a change in its magnitude, not its direction. So if this is vector v, this is vector 2v. It's twice as long, exactly the same tilt. So if alpha is greater than 0, the vector will be longer. If alpha is between 0 and 1, so here's the vector 1/2 v, same tilt, half as long, the vector will shrink. And if alpha is a negative number, the vector will stretch or shrink and go in the opposite direction. So here's the vector -1/2 v. If alpha equals 0, so if it's a real scalar number 0 you're multiplying by, or the vector is the 0 vector, then the product, alpha v vector, is the 0 vector. So make a note of which are numbers or scalars and which are vectors. I think that's the hardest part about this section, is keeping track of that. So here are some properties of scalar multiples of vectors. If you multiply by the scalar 0, any vector, you end up with the 0 vector. So that's kind of what you'd expect. If you multiply by the scalar 1, it does not change your vector. If you multiply by the scalar -1, all it does is change the direction to the opposite. But then notice, because we have two kinds of things, scalars and vectors, we need two kinds of distributive properties. So here's the distributive property that says I have two scalars added together, and then I'm multiplying a vector, and I can distribute the two scalars to the vector, and then add, and I'll get the same result. That's what the equal sign says, is the result doesn't change. But then I could have the sum of two vectors multiplied by one scalar, and this distributive property says you can also distribute the scalar over vector addition. So it's two different kinds of distributive properties because we have two different kinds of things. And then this last is the associative property of scalar multiplication, where it says if you're multiplying by one scalar and then you multiply by another scalar, you could also multiply the scalars together first and then multiply by the vector, and you'll get the same result. Okay, so that was all introductory material, and now we're to the first objective, which is to graph vectors using graph paper. So we're going to use the vectors in this figure to graph u plus v. So we're going to look at this figure over here that gives you the u vector. And I'm going to notice that the u vector, wherever it starts from, I go down 1 and to the right 2. So I'm going to go down 1 and to the right 2 and successfully transplant vector u over onto my grid. Now I look at vector v, and it's totally horizontal, a length of 1, 2, 3, 4, 5. So I need to go from the head of u, 1, 2, 3, 4, 5, and transplant vector v faithfully over onto my graph paper. So then I do the tail of u to the head of v, and that's my vector u plus v. So we'll do some more practice on this together, and we'll do these next two examples in class together also. So we use this notation with, it's like double absolute value bars, and that says we want to know what the magnitude of the vector is. So when you're doing it in your own handwriting, you're going to have to put vector notation on the v to represent the magnitude of the vector v. So we'll talk about that more in the next movie.